Okay, so this is section 7.3, which we are going to be looking at the complex numbers. So 7.3 and 7.4, we are studying complex numbers. And the reason that complex numbers are in the same chapter as vectors is because they can be analogous to vectors, and we'll talk about that in a sec. In 7.3, the main point of 7.3 is to introduce polar form of complex numbers, which can also be known as trigonometric form. Okay, so we're going to be graphing a point in the complex plane, converting complex numbers from rectangular form to polar form, and also going from polar form to rectangular form. Okay, so within the complex number system, the standard form, which can also be referred to as rectangular form of a complex number, is this form a plus bi. Okay, where a is the real part of the number and then b is the imaginary part of the number. And we can represent complex numbers in what we refer to as the complex plane. So where the horizontal axis is referred to as the real axis, and then the vertical axis is referred to as the imaginary axis. So this is not the Cartesian plane, the xy plane, this is the complex plane. And you can graph a point in the complex plane by going over to the left or right, whatever the value of A is, and then up or down whatever the value of B is to plot the point. Now remember, the real numbers are a subset of the complex numbers. And real numbers can be represented as A plus 0i, where B would be equal to 0. And then you can actually have pure imaginary numbers as well, where A is equal to 0, and you would just have bi, so 0 plus bi. Okay, so that's just what I referenced there. So the variable z is often used to represent a complex number or name a complex number. So this is still a complex number in rectangular form, just using x and y as the real and imaginary parts instead of a and b. But complex numbers are analogous to vectors because they have both magnitude and direction. So in the complex plane, or let's graph, think about this vector z being graphed in the Cartesian plane, the xy plane. Where if this is x, this is y, then this would be the terminating point of the vector x comma y. Okay, where this angle theta would be the vector z's direction, and the magnitude would be the length of the vector. Okay, in the complex plane, the horizontal axis is the real axis, the vertical axis is the imaginary axis. Let's say this is x, this is y. Then this point here would represent the complex number z. And the distance of that point to the origin is the magnitude of the complex number. And this angle here, theta, would be referred to as the direction. So the magnitude of a complex number, which is also referred to as the modulus for a complex number, you can find the same way that you would find the magnitude for a position vector. So a vector that is in that standard position where its initial point starts at the origin, and then it terminates at the point x comma y. So if we're finding the modulus for a complex number, it's just the square root of x squared plus y squared, because it represents the distance of the point to the origin in the complex plane. So if we want to find the modulus for z, it will be the square root of 2 squared plus negative 5 squared, which is the square root of 29. So if we were to plot this complex number in the complex plane, my real and imaginary axis. Okay, so 2, negative 5. So this point right here would represent the complex number 2 minus 5i. And the distance of this point to the origin is root 29. And then we'll talk about how to find its angle, or its direction angle. Okay, so x plus iy is in rectangular form, and you're easily able to identify the point in the complex plane, x comma y. Polar form of a complex number is another representation of a complex number. But because complex numbers have both magnitude and direction, when you look at a number that's a complex number that's in polar form, you're easily able to identify both the magnitude and the direction of the complex number. And then it's really easy to go from polar form to rectangular form after that. Okay, so looking at the picture over here, R represents the modulus, or the magnitude, of the complex number, and then theta represents the direction angle. So looking at that picture, R will be the square root of x squared plus y squared. We've already discussed that. And then looking at the picture, we see some familiar relationships, right? Cosine of theta is equal to x over r. Sine of theta is y over r. And tangent of theta is equal to y over x. Very familiar. Well, if we were to multiply, or let me take a step back. So right now in rectangular form, the complex number z is x plus iy. Now we can use the fact that cosine theta equals to x over r and sine theta equals to y over r to rewrite our complex number by replacing x and y. So in cosine theta equals to x over r, if we multiplied by r on each side of the equation, we would get x is equal to r times the cosine of theta. And then if we do the same thing in our sine theta equals to y over r equation, we would get y is equal to r times sine theta. So if I replace the x, I would have r times cosine theta plus I times r sine theta, where we can also factor out the r. Oops. To have r times, I have it in brackets or parentheses, cosine theta plus I sine theta. So you can easily identify the modulus of the complex number, and its direction. Now, polar form can also be referred to as cis form, where you'll see this notation used, just kind of a shorthand, and you should be familiar with that as well. And if you want to use that notation, that's okay too. Okay, so going from rectangular to polar form, this again should feel very familiar from us finding position vectors in section 7.1. So I suggest plotting your complex number in the complex plane to see basically what quadrant the complex number lies in order to help you with determining what the proper angle theta is. And then you can find the modulus, r. Okay, and find theta by using tan theta equals to y over x. So same way that we did with vectors. And then you can reference your graph of the complex number z in the complex plane to make sure that theta is in the appropriate quadrant, the proper quadrant. And then you have everything necessary in order to write your complex number in polar form. Okay, so first graphing z in the complex plane. Very important to label your axes. That's one, let's say negative root 3 is down here. Okay, so we need r and theta. Okay, so to find r, which you can also use the absolute value bars for that notation, it'll be the square root of 1 squared plus negative root 3 squared, which will end up being the square root of 4. So 2. And for tan theta equals to negative root 3 over 1. Now, negative root 3 is an angle, negative root 3 is a ratio of tangent on the unit circle. So you could look at this as a trig equation that you could solve. So you go, okay, well, we're in quadrant 4. So for what angle on the unit circle is tangent equal to negative root 3? And that would be 5 pi over 3. Or if you used inverse tan, okay, inverse tan, I'm going to say it's theta asterisk, inverse tan of negative root 3 over 1 will end up giving you negative pi over 3. It'll end up giving you this angle, where you would then want to add to pi to find theta that's in standard position. So inverse tan of negative root 3 plus 2 pi would give you the 5 pi over 3. Okay, so then once we have the angle, and the modulus, we can go ahead and write the complex number in polar form. Now I used radians. I did not specify here radians or degrees, so you can choose if you're not specifically asked for an angle in degrees or radians. You can choose what you're more comfortable with. Hopefully radians. In cis form, this would be 2 cis 5 pi over 3. Okay, and we talked about this because inverse tan, remember, will give you an angle between negative 90 and 90 degrees, or negative pi over 2 and pi over 2 degrees, which is quadrant 1 and quadrant 4. If your complex number is in quadrant 2 or quadrant 3, then you're going to need to add 180 degrees to the inverse tan. Okay, so let's first graph in the complex plane. Okay, so we want to find r and theta. R will be the square root of negative 1 squared plus 2 squared, so root 5. Okay, so tan theta equals to 2 over negative 1, so negative 2. We are going to have to use inverse tan. Okay, and because we're taking the inverse tan of a negative ratio, that's going to give us an angle, a negative angle from quadrant 4. Okay, so, and then since that will give us a negative angle from quadrant 4, theta will be inverse tan of negative 2. I'm sorry, my cat's yelling at me to feed her. Inverse tan of negative 2 plus 180 degrees, which is approximately 116.56 degrees. 0.56, I think that's 560 degrees. Sorry, I don't have my calculator with me right now. So then z is root 5, and in brackets cosine of 165.560. I apologize if that's rounded incorrectly. I'm going off of the notes I already have written. I sine 116.560 degrees. And there we have our complex number written in polar form. Super easy to go from polar to rectangular form. You just evaluate the trig functions and simplify. So here, cosine of 210 degrees. Okay, 210 degrees is on the unit circle in quadrant 3. That's negative root 3 over 2 plus I times negative 1/2. And then distributing the 2 in, we'll have negative root 3 minus I. Done. Rectangular form. 35 degrees is not on the unit circle. So I'm going to distribute the 4 in first. And then I have to use a calculator, and I get 3.276 plus I times 2.296. So in this case, rectangular form ends up having to be an approximation of the complex number, but polar form, it's the exact value of the complex number, or the exact values for A and B. Okay. So your test is going to be on section 7.1, 7.2, which is vectors, and then this introduction to complex numbers in 7.3. And then we will finish up talking about complex numbers after spring break.